All right, in this video, we're going to talk about a new concept called the electric field. What have we done so far? We've talked about the Coulomb Force, which we've said is expressible thusly. Where Q1 and Q2 are two charges, R12 is the distance between those two charges. And that distance is squared. Now, this is a vector quantity, it's a force. I'm not writing down the vector nature here for simplicity. But remember, this is a vector quantity, and anything I do to it is going to have to take the vector nature into account. So we're gonna hang on to that in our minds for just a second. So this is the force that exists between two charges. Okay, fair enough. If I have two charges, Q1 and Q2, I have a force, but what happens if I just have one charge? Well, there's clearly not a force there, but it does not necessarily make sense to say that because there's no force, nothing physical is happening. In some sense, maybe that's the case, but what we can say is that Q2, or any Q you want to put here, really doesn't have to be this specific Q2, any charge, is going to exert an influence on the space around it. If I put another charge into that space, that influence will then manifest itself as a force. If I don't put another charge, there will be no force, but there's still an influence on the space around this charge just due to its presence. Just like the presence of mass influences the space around it. If I put another mass in, that influence manifests itself as a force. But in this case, I want to talk about how to characterize the influence of just one charge instead of the two charges that will give me a force. So let me write this new expression in this new quantity. E is going to stand for electric field. A field is the way that we talk about the influence on space of some quantity. You might have mentioned a gravitational field in Physics 1. If you didn't, that's okay. I know you talked about gravity, but we can talk about gravitational fields. Now we're going to talk about electric fields. What I'm going to do is I'm going to write down something similar to this expression, but a little simpler in that I only have one charge now, because that's what I'm trying to get to, the influence of one charge. And that's going to be divided by some distance squared. Now, you might notice there are no subscripts here, right? I don't have charges 1 and 2 now, I just have one charge. So the subscript 1 doesn't make a whole lot of sense because that's all I have. What might not make sense though is the subscripts here. This was the distance between these two charges. Now I don't have another charge, and so I've got to redefine what that R is. That R is now the distance between this source charge here, that is the source of this electric field, and an arbitrary, which means I choose it, observation point. An arbitrary observation point. So if I'm trying to characterize the influence on space of this charge, right, I have this charge Q, my source charge, right? Then I might choose this point to, I want to know what the influence is here. I might want to know what the influence is here. I might want to know what the influence is here. Right? Each of these is a different R, and this is some distance 1, maybe this is some distance 2, and this is some distance 3. So if I'm going to determine what the influence is here, I would plug in this specific distance here, this specific distance for this point, this specific distance for this point, and so on and so forth, right? Of course, that is going to become tiresome after a while, plugging in individual points. What I'd really like to know is a functional form for how this applies to all points, which is why this is now a general quantity, right? This is a very specific quantity, although it is a variable, depending on how far these two are apart. But this is a general variable now for any distance away from that source charge Q. And so this actually is the functional form of what I'm going to call now my electric field. If you want to make this a vector, which of course we will eventually, we can just add the vector nature here and put a placeholder unit vector here. Again, that will take different forms depending on what coordinate system you're in. If you're in a spherical coordinate system, it's going to look like R. If you're in Cartesian, it'll be an I hat, J hat, X hat, if that language makes sense to you. It's going to be some sort of unit vector to show you the vector dependence. So what we've arrived at from just thinking about the concept of a force between two charges is a field, which is the influence due to one source charge. All right, so now that we have that, let's ask ourselves, how can we relate this to what we already know? So I have one charge, right? Some charge Q, and I know that charge Q is producing an electric field. Well, I'll just keep it as E, producing an electric field. So I will subscript this with an S for source. This is the source charge. Now, let me bring another charge in. All right. I'm going to call this Q sub T for test. We don't use T for much in physics besides time, but I'm going to just, some test charge, right? I want to test out what the electric field is, so I'm going to bring in a test charge and put it at some distance, right? Well, I know now that I can characterize the force between these two as this, K, Q source, Q test, over that distance between source and test squared. Right? But notice, I already have here what I've circled. This is the electric field due to this source charge evaluated at a particular point given by the location of the test charge. So while nothing is wrong with this, there's a shorthand way to write this. If I already have the field, like if I was given the field, which I know it consists of the source charge and some distance in the Coulomb constant. If I already have the field, I can now rewrite this as E, Q, T. And if I don't even need to know what the source charge is, if I was just given, here's this field has this value, right? I can dismiss the subscript and write this generally as EQ, as long as you understand that this Q is the charge you're placing into the field that existed due to some other charge, right? And we're just trying to get rid of the subscripts to make it all clean. So I can now write the Coulomb force as the product of some charge that I'm putting into an electric field. This is really, really handy because very often you don't know the actual charges from which the field arises, right? You can, of course, if you're given a charge, you can say, okay, well, this is the electric field due to this charge. I have that here. But very often, that's really, really complicated. What if you're not given just one charge? You're given 7 charges, or you're given 1 billion charges, or you're given a continuous distribution of charges, right? Determining the electric field can be significantly difficult. We can still do it, but it can be significantly difficult. However, if someone else has already done that work for you, and they just tell you what the field is, then if you just put a charge into that field, you get a force. And so we have 2 ways to determine the force here. The first is the full Coulomb expression. I'll write this down. The full Coulomb expression, Q1, Q2 over R12 squared, also expressible as EQ. So which one of these 2 you use just depends on what you have. If you're given 2 charges, you're probably going to need to go with this guy. If you're given an electric field without reference to some charge, and you put a charge in it, you're going to use this. They both give you a force, but which one you use just depends on what you're given. What I do want you to notice, though, is very often you will just be given an electric field without reference to the source charge. That does not mean there is no source charge. If there's a field there's a charge. You might not care about what that source charge is, but if there's a field, you're guaranteed that there's a charge. That also works the other way. If there's a charge, you are guaranteed that it's producing a field. Okay. One other thing we need to talk about fields is units. Let me take the outer portions of this. Right? Let me get the field by itself, just a little mathematical wizardry here. This is how we interpret the electric field. It is the force per unit charge, right? Units of that are going to be newtons per Coulomb. All right, so if you take a field and you put in a charge, if you take a field and you put in a charge, you get a force. That is this expression here. Some charge in a field gets a force here. That force is determinable because the units here are newtons per Coulomb. So a particular amount of coulombs gives you a particular amount of newtons.